Hello everyone, in this video we'll discuss Bernoulli equation and Bernoulli principle, which is continuation to the dynamics of fluids. If we take a fluid element in a pipe, as you see here, and assume this fluid element is going through a certain region of the pipe to another region that has different height and different pressure. Let's assume in this region the pressure applied on this fluid element is in the positive x direction, while on the second region the pressure is opposing the flow of this fluid element. What would be the net work done on this fluid element throughout its flow? Now we can see three forces and hence three work equations associated with those three forces can be stated. And recall the work done is force times displacement. So the work done in the first region is the force applied by an external source that caused the fluid to flow, and as we know, fluids do not flow unless there is force acting on them. So F1, that's the force that is acting on this fluid and causing it to flow from left to right, times the displacement of that fluid during its presence in region 1. And we can replace the force by pressure times area, since we know that pressure is defined as the force per area, where the area is the sectional area of the pipe in region 1. Now when the fluid reaches region 2, it's encountering opposite pressure, so the force is negative because the force here is opposite to the motion, and we know any forces opposite to the motion will produce negative work because it's dissipating energy. If we replace the negative force here by the pressure times area, it will be negative P2 times A2, where A2 here is the sectional area in this region of the pipe, region 2, times delta x, where delta x is the displacement of that fluid element that corresponds with the same volume of the fluid element in region 1. And recall that the volume of the fluid does not change as long as the fluid is incompressible. Now the third work done on the fluid is a negative work by gravity, because here the fluid is going against the force of gravity. So the force of gravity is downward while the displacement is upward. And hence the work done by the gravity will be the weight times the change in the vertical position, y2 minus y1. So those are the three work equations that are applied on this fluid element during its flow in this pipe. So we can combine them together and find the net work, and this will be the equation of the net work. Now recall that the net work is the change in the kinetic energy. This is one of the important equations that we learned during our study of the work energy theorem. So now if we set those two equations equal to each other, so we have the change in the kinetic energy on the left hand side, which will be 1/2 mv2 squared, that's the final velocity v2 in this region, region 2, minus the kinetic energy in region 1. This is equal to the net work done on the fluid element. Now as we said, v1 is equal to v2. This is the case with incompressible fluid. Hence we can take the mass in the change in the kinetic energy equation to be equal density times volume. This came from the equation density is equal mass over volume, so we can write mass in terms of density and volume. Now since volume is the same, and here the volume will be the area times the height of this fluid element, which represents kind of a cylinder, and we know the volume of the cylinder is the sectional area times the height. So here A1 times delta x1 is actually equal to A2 times delta x2, and hence we can replace the mass by density times area times delta x, for A times delta x will replace the volume. And now we set the two sides equal to each other, and notice here that A2 delta x2 is the same as A1 delta x1. Now if we take the kinetic energy and the work done per unit volume so that we can cancel A delta x, so we divide the whole equation by A delta x to obtain the work energy done per unit volume, and this will reduce the equation to the following. If we rearrange it so that everything has to do with region 1 will be on the left hand side and everything has to do with region 2 on the right hand side, we get this equation which we call it Bernoulli's equation. This is assuming that region 2 of the pipe has different vertical position. Now if we are dealing with horizontal pipes, then y1 will be equal to y2, and this part will be cancelled out, and we'll have this equation. Now notice in this equation that the velocity and the pressure are related to each other, meaning if in region 2 the velocity increases, the pressure has to decrease in order to maintain the equality. And the same thing, if the pressure happens to decrease, the velocity has to increase to keep the equality. This has very important implications, especially in airplanes, science, and aviation. Okay, now as you see here, 1/2 rho v square represents the kinetic energy per unit volume, because density is mass per volume, and rho gh represents the potential energy per unit volume. Here we replace m by mass over volume, because again density is mass over volume. And the sum of those three terms, pressure, kinetic energy per unit volume, and potential energy per unit volume, have constant value along the streamline. If you add them at any point in the streamline, they will give you a constant value. This is an important implication, and this will bring us actually to those two final conclusions, which are very important. When the velocity of a fluid is high, the pressure will be low. So increasing the velocity will decrease the pressure. And vice versa, when the velocity is low, the pressure will go up, will be high. This has very important implication in airflow and lift. If we take here a segment of the airplane wing, if you look at the wing, the way it's shaped, it allows longer path for the air above the wing than the length of the path of the airflow below the wing. And that will create bigger velocity since the distance is longer, hence the velocity of the air above the wing will be faster than the velocity of the air below the wing. Remember, velocity is distance over time, so here the time is the same. The time taken for an air element to go from this point to this point is the same as the time taken for the same volume of the air element to go from this point to this point. But the distance is bigger above the wing. This will constitute bigger velocity. And bigger velocity means lower pressure. So the pressure above the wing is lower than the pressure below the wing. Recall that the faster the fluid, the less the pressure. We know that forces always go from the high pressure area to the low pressure area. This is how winds are generated. When you have two areas that have different pressure, air tends to try to balance the difference in the pressure by moving from the high pressure area to the low pressure area. So the same thing happened here around the wing. So since the air is moving faster above the wing, then you have low pressure area above the wing, while the pressure below the wing is higher. Hence a force will be generated to push the air from the high pressure area to the low pressure area, and this force is the force of lift that causes basically airplane to be able to take off and create the lift force. And also this same concept of faster velocity, low pressure can explain why a spinning ball can curve, because when the ball is spinning, it's creating pressure against the air. Like assume here this ball is moving in this direction, V, and this is the direction of the airflow. The airflow is in this direction. And now if it's spinning counterclockwise, it's creating friction with this air that is hitting it. Remember that air has the ability to apply friction, as we learned earlier. So this air here is encountering friction with the ball, which will slow it down, because here the spinning is opposite to the motion of the air. So here the air will be moving slower, and hence you have high pressure area than this area, where actually the direction of the spin is in the same direction as the fluid, the airflow. So the speed here will be bigger of the fluid than below the ball. So here you'll have high pressure area below the ball, while you'll have low pressure area above the ball. And as we mentioned, the force is always moving from high pressure area to low pressure area. So a deflected force in the upward direction will be applied on this ball. And the same thing here can be applied if the ball is spinning sideways. In that case, it will curve sideways as well, and that explains why spinning ball can curve. Okay, in this problem, we are given the pressure in the first region, the first part of the pipe, the diameter, and the velocity. And we are asked to find the velocity and the pressure in the second part of the pipe that has less diameter, which is now 3.5 centimeter. Now, if we go directly to Bernoulli equation, we'll see that we have two unknowns. Notice here that this is horizontal pipe, hence Bernoulli equation will be P1 plus 1/2 the density, and this will be the density of the water times the velocity of the fluid, which is the water square, equal to P2, the pressure in the second part of the pipe, plus 1/2 the density times the speed in the second part of the pipe squared. Here we have two unknowns, P2 and V2. So we cannot solve using one equation, we have to go to a second equation. And if you recall, continuity equation provide a venue to solve for the velocity, because we know the A1, V1, where A1 is the section area, the sectional area of the pipe in the first region, times V1, which is the velocity of the fluid in the first region, equal to the sectional area of the pipe in the second region times the velocity in the second region. And we know that this equation also can be written in another format, which is d1 square instead of a1, d1 square, which is the diameter in the first region of the pipe, times v1 is equal to d2 square times v2. And now we can go ahead and plug the numbers. d1, diameter in the first region, 0.08 meter. We can keep it as centimeter because centimeter eventually will cancel out, but it's a good habit to change all units to meter, kilogram, and seconds. So go ahead and write it as meters, 0.08, and this is meter squared, times V1, which is 4 meter per second. This is equal to the second part of the equation, which is the diameter in the second part of the pipe, which decreased to 0.030 meter, converting centimeter to meters here. This is squared, times the velocity which we need to find. And now we solve for V2, and if you solve for V2, this will give you 20.9 meter per second. So this is the speed of the fluid in the second region of the pipe, and we expect V2 to be bigger than V1 since the sectional area has decreased. Now in the second part, we need to find the pressure in the second section of the pipe, in the smaller section of the pipe, and here we'll apply Bernoulli equation. So here, we'll take it and plug it here. So P1 is 2.50 times 10 to the force 6 Pascal. Pascal is Newton divided by meter square, plus 1/2. And here the density is the density of water. This is water, and here this is water. And water is 1000 or 10 to the power 3 kilogram per meter cube, times the speed of the fluid, which is 4 meter per second in the first part of the pipe, and this is squared, equal, now the right hand side has P2, which is the unknown, plus 1/2 times the density of the water, times the velocity of the water in the second part of the pipe, and that part we evaluated in the previous, in part A, whole square. And now if you carry out the calculation and solve for P2, P2 will come out to be 2.29 times 10 to the power 6 Pascal. And you can see here P2 is less than P1 as we expect, because the speed of the fluid increased, and when the speed of the fluid increases, the pressure should decrease. Okay, in this problem, which is similar to the previous problem, the only thing here you are given the size of the pipe in the second region in terms of the size of the pipe in the first region. We are told that the radius constricts to 2/3 of its original size. Okay, and again we are asked to find the speed of the fluid, which is water, in the second section of the pipe, and the pressure. So basically we follow the same steps. We apply the continuity equation, but notice here that R2 is given to be 2/3 R1. So now when we apply continuity equation, we can use the radius in that case, R1 square times V1, where R1 is the radius 1 of the pipe in the first section, times the speed of the fluid in the first section equal to R2 squared times V2, where R2 is the radius of the pipe in the second section, times the speed of the fluid, which is water in the second section. Okay, now we plug the values. R1, we'll leave R1 as it is, R1 squared times V1, where V1 is 2.75 meter per second, equal to R2 squared. Now we replace R2 by 2/3 R1 from this formula, 2/3 R1, and they are all squared times V2, which is our unknown. Now notice here that R1 square will cancel out with R1 square. Let's go and simplify the equation further here to see that. So we have R1 square times 2.75 meter per second equal to 2/3 square. 2/3 square is 9/4 times R1 square times V2. Now you can see here R1 square on the right hand side would cancel out with R1 square on the left hand side, and we can solve for V2, which is 4 times 2.75 divided by 9, and this will yield 6.19 meter per second. As we expect here, V2 is bigger than V1 because the area of the pipe has decreased, which will increase the velocity of the fluid. Okay, in part B, we'll go ahead and this is horizontal pipe, so we don't need to include the change in Y. So P1 plus 1/2 for here the density of water times V1 square equal to P2 plus 1/2 for water, and this is V2 square. And now we can go ahead and plug the values. P1, the pressure in the first region or the first section of the pipe, is 1.20 times 10 to the power 5 Pascal plus 1/2 the density of water, which is 10 to the power 3 kilogram per meter cube, times the speed of the fluid square, that's 2.75 meter per second all square. This is the left hand side equal to the right hand side, which is P2, our unknown, plus 1/2 times the density of the fluid times the speed of the fluid, which we found to be 6.19 meter per second in the previous part. And now we solve for P2, and if you carry out the calculation here, 1/2 times 1000 times 6.19 all square, this should give you around 19,142.578 Pascal, and 1/2 times 1000 times 2.75 meter per second square, this should give you around 3,781.25 Pascal. So now P2 will be 1.05 times 10 to the power 5 Pascal. And as you see here, P2 is smaller than P1, as we expect, because the velocity has increased. When the velocity increased, the pressure will decrease according to Bernoulli principle. Now, one of the applications of Bernoulli principle in medicine is the case of arteriosclerosis, where artery could be narrowed down by buildup of plate in the vessel. This is especially critical when 80% of the vessel is constricted, meaning you are left only with 0.2 or 1/5 of the area of the vessel to channel the blood. Now consider that the speed of the blood flowing in a healthy vessel is 50 centimeters per second, and that the density of the blood is around 1.06 times 10 to the power 3 kilogram per cubic meter, which is a little bit denser than water. Now let's try to find the speed of the blood in the unhealthy vessel and also the change in the pressure. So to solve the problem, so since we have two unknowns, Again, we'll start with the continuity equation, and we can write A2 in terms of A1. A2 is 0.2 A1, or 1/5 of A1. So on the left-hand side, we have A1 B1, and on the right-hand side, we replace A2 by 0.200 A1 times B2. And you can see here A1 will cancel out, and hence B2 is 1 over 0.200 times V1. Since V1 is 50 centimeter per second, which is 0.5 meter per second, hence V2 would be 5 times 0.5, because 1 over 1/5 is 5, and this will yield 2.50 meter per second. So as you see here, the blood will increase its speed whenever it enters the low area vessel. Now in part B, we are asked to find the change in the pressure, delta P. And we know delta P is P2 minus P1. So now if you look at Bernoulli equation, which is P1 plus 1/2 the density of the fluid, in that case the blood, times the velocity in the first region square, this is equal to P2 plus 1/2 the density of the blood times its velocity in the second region square. And now we rearrange the equation to solve for P2 minus P1. So we can move P1 to the other side, and then move 1/2 for P2 squared to the other side. So we have P2 minus P1 equal to 1/2 the density times V1 squared minus 1/2 the density times V2 squared. We can take 1/2 the density as a common factor. So P2 minus P1 is equal 1/2 the density times V1 squared minus V2 squared. Okay, and we can go ahead and plug the values. So P2 minus P1, P1/2 times the density of the blood, which is 1.06 times 10 to the power 3 kilogram per cubic meter, times V1 squared, which is 0.5 squared, minus V2 squared, which is 2.5 squared, and this is meter square over second square. And if you carry out the calculation, P2 minus P1 will come out to be negative because P1 is bigger than P2. It's negative 3.2 times 10 to the power 3 Pascal. What that tells us, this means that the blood pressure decreases. That's the meaning of negative here. The blood pressure decreases by this amount, by 3.2 times 10 to the power 3 Pascal when it enters the unhealthy vessel. Okay, in this last problem, we have a building where the water will be elevated to reach certain faucet in the building. So we have here the factor of the change in the height. Now we are given the pressure in the first region, or the first section of the pipe, which is at the street. We are given the speed of the water, and we are given the diameter of the pipe to be 0.05 meters. Then we are given the diameter of the pipe in the second section. We are given the elevation, which is 20 meters, that's Y2. And we are asked to find the velocity and the pressure. So we are asked to find V2 and P2. So again, we need two equations. So we'll start with the continuity equation. And since we are given the diameter, so we can write it in terms of diameter. D1 squared times V1 is equal to D2 squared times V2. And now we plug the values and make sure to convert. And it's up to you to convert centimeter to meters, because here actually the centimeter will cancel out anyway. I'll go ahead and convert it. So we have 0.05 meter squared, that's the diameter in the first section of the pipe, times the velocity, which is 0.6 meter per second. This is equal to the diameter in the second section of the pipe, which is 0.026 meters squared, times V2, which is our unknown. And now we solve for V2, and if you carry out the calculation, this will give you 2.22 meters per second. As you expect, the velocity has increased in the second section of the pipe, as the radius decreases. Now for the pressure, we'll apply Bernoulli equation. And now we have to apply the full equation that includes the height, so P1 plus 1/2 the density of the fluid, which is water, P1 square, plus OGH1, where H1 is the height in the first region, or the first section of the pipe, equal to P2 plus 1/2 the density of the fluid, times V2 square, plus the density of the fluid times G times H2. Now notice here that at the street, the height is 0, so this part of the equation is 0. And here in this part, H2 is 20 meters, as we given in the problem. The elevation is 20 meters. The elevation of the pipe is 20 meters. So now we can go ahead and plug the values. For P1 is 3.85 times 10 to the power 5 Pascal, plus 1/2 the density of the water, which is 10 to the power 3 kilogram per cubic meter, times 0.6 plus 0, equal to P2 plus 1/2 the density times the velocity square plus the density times the acceleration due to gravity times the elevation, which is 20 meters. Okay. Now you can go ahead and solve for P2, and if you carry out the calculation, this will give you 1.87 times 10 to the power 5. Now as you see, this value is less than P1, and that's because when the velocity increases, the pressure always decreases.